Hello everyone! In this video we will continue to examine topic 5.1 electric fields and the idea of electric current. Now, the concept of the electric current is sometimes a little bit tricky. In the vast majority of cases, we're going to consider the electric current as it simply flows within a wire or ultimately within a circuit. But the essence of the idea of the electric current is simply that charge is moving back and forth. And this example, which you're welcome to sort of work through once I describe it, is designed to sort of hammer that point in. Okay, so in what's called the shuttling ball experiment, you take a metal conductor or a metal ball, usually pretty small, imagine sort of a tiny ball of aluminum, held on a very thin string that's insulated, and then you put a positively charged plate, a plate with a whole bunch of positive charges over here, and negatively charged plate over here, and then you connect this to some kind of sensor. We'll discuss exactly what a little bit later on. And what will happen is that that ball will actually shuttle back and forth, okay? And let's think about why for a second. Let's just give a qualitative explanation. So if you take a metal ball right here, well, when it touches this positively charged plate, some of the electrons on the metal ball will be attracted to that positively charged metal plate and will flow out. That will give this metal ball a positive net charge. Then that positive net charge metal ball will feel repelled from the positive plate and go to the negative plate. It will then touch the negative plate. When it touches the negative plate, that positively charged metal ball will attract electrons from the metal plate into the ball itself until the electrons in the ball itself repel the ball from the plate. At that point, the ball then is attracted to the positive plate and repelled from the negative plate and swings back to the positive plate, at which point the whole process happens again. And in real life, if you set this up, that little metal ball will often bounce back and forth pretty quickly between these two plates. In particular, it shuttles charge from the positive plate to the negative. It shuttles positive net charge from the positive plate to the negative, or equivalently, it shuttles electrons from the negative plate to the positive plate. This shuttling ball is not what we would normally consider as electric current. It's not our normal idea, but it meets the definition, and you can in fact calculate it as you were asked to do in this particular example. Why? Because charge is transferring over time from this area to this area, or vice versa, and as a result, there's a current. You could calculate the amount of charge and divide it by the amount of time that it takes, and that'll give you the current. And that's what this worked example is about. But the big picture is that this kind of situation counts as electric current. If you have charge moving back and forth, that's an electric current. If I take a charged metal ball, pick it up with my hands, and walk it over to the other side of the room, that's an electric current. Now, admittedly, it's not a very strong electric current, as you would find out if you did the calculation. But it is an electric current, and it's important to sort of keep that in mind as we move forward. Now, as I mentioned, picking up a metal ball and moving it from place to place is not going to produce a very strong electric current, but we can still ask, how fast does the current move? Okay, in this case, we're sort of asking a generic question like you would for water. So if a river current were flowing, notice I just used current flowing, but so be it. If a river current were flowing, you could ask, well, how much water is moving and how fast are the water particles moving? And we have to be a little bit careful, though, with electric current because there are actually 3 separate speeds for electric current, depending on what you mean by fast or by speed. Okay, so there are 3 different things going on, and we need to keep them straight. So the first thing is that within the wire, ignoring the current for 1 second, so ignore the current for a second, the electrons inside the wire, in the sea of electrons, right, the wire is made of metal, are bouncing around, and they're moving randomly due to thermal energy. Okay, there's random kinetic energy associated with these particular particles at temperatures that are higher than absolute zero, and as a result, because they can move, they do move. And in fact, they move with very, very fast velocities. So they are bouncing around sort of inside that metal lattice at velocities close to the speed of sound in that particular metal, roughly 1 × 10⁵ meters per second or thereabouts. And that's random. So they're bouncing all around inside the wire. Okay? This speed is not what we usually mean when we say how fast does the current move, but it is probably the best answer to the question, how fast are the charges moving? That is, how fast are the electrons moving? That's the thermal speed. Okay? Now, when an external electric field is applied, however, they drift, they drift on net with an extra velocity. So not only are they bouncing around, but there is a net extra velocity that sort of adds vectorially to whatever previous velocity they were already going. Okay, that's shown in blue, thermal speed shown in blue, and then the electric field velocity, that extra velocity provided by the electric field, is shown in green. That's known as the drift speed. And the electrons in the wire, while they're bouncing around, all have a tiny little net velocity against the direction of the conventional current. All right, so all the electrons are sort of very slowly drifting this way as they bounce around randomly very fast. It's important to note that you can measure and calculate this drift speed, which we'll see separately from the thermal speed. So, 2 speeds so far. One is the speed with which the electrons are sort of bouncing around inside the wire. That's the thermal speed. This drift speed is going to be sort of our and the IB's answer to the question, how fast is the current moving? It's the speed associated with the electric current itself. It is what is related to that applied electric field that is producing the current. It is also worth noting the drift velocity is very, very, very slow. We're talking on the order of 1/10 of a millimeter per second, as compared to this thermal speed of 10⁵ meters per second. This strikes us as kind of absurdly fast until we remember, yes, these are tiny, tiny, tiny particles in that metal lattice. Okay, tiny particles moving very fast. This strikes us as somewhat absurdly slow, because if this is the speed of the electric current, how do we do things like turn on the light with a switch, right? This is the speed of the electrons, the extra speed contributed by the external electric field producing the current. Well, as it turns out, there's a third speed, what I'm going to call the signal speed. Okay, this is the speed of you flip the switch on your wall and the light turns on. It's the speed of that thing. Okay, so when a signal is sent via electricity, the effect of the applied electric field travels faster than the particles themselves actually travel. So you can imagine this, think about like a wave at a sporting event, okay? People stand up and down to produce that wave. Now the wave in the actual bowl of the stadium is moving much faster than any individual person could possibly be moving. That wave speed is actually way faster than a person sort of running on the outside of the stadium. This is a very similar thing. So the effect of the applied electric field when you turn the switch is actually faster, but not instantaneous, than the electrons are moving themselves. That's known as the signal speed, and it's about the speed of light. Strictly speaking, it's slower than that, but it's not much slower. It's in the same ballpark. And it travels about as the same speed as an electromagnetic wave within the conductor itself. about 1 times 10 to the 8th meters per second. Now, when the IB is going to ask you for the speed of the current, they mean this thing, the drift speed. But it is important to keep these three ideas separate, particularly because our calculation for the drift speed gives us a speed that seems absurdly small compared to both the signal speed and the thermal speed. Now, how do you calculate the drift speed? Okay, this is actually a fairly straightforward calculation. So this diagram is just repeating that diagram here of the drift speed. And to calculate it, we're going to consider a current with n charge carriers per unit volume. Okay, n charge carriers in a wire, we're just talking about electrons. Although you could discuss the drift speed of an aqueous solution, for example. So n charge carriers, electrons in a metal, and that n charge carriers per unit volume is known as the numerical charge density. So not the total charge density, that would be coulombs per meter cubed. This is just the number of charge carriers per unit volume. If you had 10 electrons, this would be 10 electrons per meter cubed. Although that would be a very big wire, I suppose. If you have a current with n charge carriers per unit volume, and in delta t, in some small unit of time, delta q passes, then let's calculate the current. The current is delta q divided by delta t. Now, what is the total charge that passes in that amount of time? Well, it'll be the number of charge carriers per unit volume times the charge on each of them. They're all moving a little bit. Times whatever that volume is. So remember that if it's the number of charge carriers per unit volume, then n times delta V is equal to the number of charges, and then Q is the charge per individual charge carrier. So this delta V, though, that's the volume, as shown right there. That's equal to the cross-sectional area of the wire, okay? So that cross-sectional area shown in A here, times delta X. So we blow this particular picture up, and we see that it is the cross-sectional area A times delta X, that's in yellow, and that's the volume that we're talking about within a certain amount of time, delta T, okay? Then we note that the drift speed V, okay, the speed, is how much delta X per delta T is traveled. So, like, what volume are we actually talking about? Well, it's the volume here, delta V is A delta X. That distance that the sort of ring associated with the cross-sectional area goes, right, if we're counting the electrons as they move this way, is delta X. And so the drift speed V is equal to delta X divided by delta T. All right, so we go back here, we take this equation, we plug it in. That delta X over delta T is the drift speed. And that gives us our equation for the drift speed as it's related to the electric current. I is equal to N, the numerical charge density, times Q, the charge per charge carrier, times A, the cross-sectional area of the wire, times V, the drift speed, okay? Big picture. As these things go, this particular equation is not, I think, particularly revealing, but it is a nice opportunity to get some points for some plug and chug. So if you're thinking about just collecting some points, this particular equation is in this subsection, and the questions tend to be a little bit plug and chuggy. They will give you some combination of these variables and then have you find one of the others. Just fair warning, these equations, or this particular equation, will not have much application outside of this context, but it is some nice points if you identify that the IB is asking for the drift speed at some point. And usually if you're calculating the drift speed directly, you will then take the current that you're given and divide by N times Q times A. And obviously you need to be given all of these quantities. So There are a couple of examples which show this. Note, they will almost never give you the cross-sectional area directly. They will end up having you calculate it by giving you the radius of a circular wire or thereabout. You have a few examples here to test your knowledge of that.